Next up, a discussion of subspaces, span, and the notion of linear dependence and independence. This is sections 2.2 and 2.3, and we'll take about a day and a half, maybe 2 days to go over. So let's start with a discussion of the notion of subspace. So a subspace is the following. You have V is a vector space. And suppose you have a subset of the vector space, but it's not just any old subset. It's a subset which is a vector space in its own right. That's the notion of a subspace, also a vector space. So, for example, if V is R2, an example of a subspace would be a line through the origin, W. Because W is basically a copy of R1, the real lines, sitting inside R2. And just to bump that example up by one dimension, suppose V was R3. An example of a subspace in R3 is, for example, a plane through the origin. And this is, of course, intended to extend off to infinity. And you're supposed to think of a plane through the origin at any angle. Now, those are sort of maybe typical examples, but there are some more obvious examples that I've skipped in a sense. So, for example, in R2, an example of a sort of a silly example of a subspace is just the origin. 0 is a subspace. And another example is all of R2 itself. So you can see that a subspace can have any dimension from 0 to 1 to up to the dimension of the bigger space. So for example, in R3, if you have W is a subspace of R3, then W is a vector space of dimension equal to 0, 1, 2, or 3. Okay, so let's say that a little bit more carefully. What exactly is a subspace? So suppose V is a vector space, and you all know what it means to have a subset of a set. So suppose you have a subset. What does it mean for W to be an actual subspace? That's a more refined property. You say that W is a subspace if, well, what I said was that W is a vector space in its own right. And if you think about it, what that means is just two properties. If W1 and W2 are in W, well, you can add them. W1 plus W2, you've added them in V. This is a vector in W, so it's also in V. So think of this as a vector in V, and this is a vector, and W2 is a vector in V. And so when you add them, you get a vector in V, and the requirement is that this vector actually winds up in W. And the second condition is similar with respect to scalar multiplication. If R is a real number and W is in W, well then R times W is a new vector in V, and the requirement is that this is supposed to be in W. And well, that's in some sense a lemma or a proposition and not a definition, but it's true, and you can take this to be the definition. This is proposition 2.9 in the book, and what it means is that what happens is, all I'm saying is that if this holds, then if you take W with addition from V and scalar multiplication also from V, this itself is a vector space, is, excuse me, a vector space. Okay, so let's do one or two more examples with this more precise definition in mind. So let's take our very first example, take V as R2, and take W to be this line through the origin. And I claim W is a subspace. Why is that? Well, I have to check two things. If I have a vector in W and I have another vector in W, if I add them, W1, W2, if I add them, the result is W1 plus W2, and they're all pointing in the same direction. This new vector is also in W. And I also have to check, I'll draw an example in this other property in the other direction. Suppose I have a vector W, and I have a scalar, say, 2, and I multiply 2 times W. I want that to still be in the same space, and well, it is. 2 times W is also along this line. So let's do a non-example. Let's take an example like this. Let's take this to be W. Is this a subspace? Well, let's see. I have to check the addition property. So I have to check that if I take a vector in in W. So what does that mean? So this vector right here means this arrow pointing from the origin. That's W1. And suppose I took W2 to be this point on the line, which means this vector W2. Well, when you add them, you're way out here in space. What you get is W1 plus W2, and that's not in W. So this W is not a vector, is not a subspace. And it doesn't satisfy the scalar property either, and it actually fails that in a rather bad way. Suppose W was in W, and I took the scalar R to be 0, the number 0, then R times W is equal to what? If you multiply any vector by the number 0, you get the 0 vector. And so if W were going to be a subspace, it would have to contain the 0 vector, but it doesn't. We missed 0 here. So that's an easy check, and that's always true. Any subspace must contain the 0 vector. Now, there's one point here which it's good not to get confused about. This W is a straight line. So this W here, it's W is a line, a straight line, and so you could make W a vector space if you ignored the R2 that you're sitting in and you just thought of W as being the line. That's a vector space. The crucial thing is that the addition of vectors in that vector space is not the one coming from sitting inside R2. So adding these two vectors, if you did make W a vector space, when you add things, they'd all be pointing in along the direction of the line, and that's perfectly fine. But when this thing's sitting inside R2, when you're adding things, they're sticking in the wrong direction like this. So just because this is a straight line and can be thought of as a vector space, that's not enough to make it a subspace. Let's do a few more examples. Let's look in R2 again. And I mentioned that just taking the zero vector, just the zero vector itself is a subspace. So I'm going to say let W be just the set consisting of a single vector, the zero vector. I say that this is a subspace, sometimes called the trivial subspace. Well, what do we have to check? We have to check if you add any two vectors in that set, you get another vector in the set. Well, there's only one vector to choose, so the only thing that you have to check is that 0 plus 0 is also in the set, which is to say that had better be equal to 0, which is surely true. And you also have to check that if R is any real number, and you multiply it times the 0 vector, then you get another vector in the set, which is to say you better be getting the 0 vector. And is that true? If you multiply the 0 vector by any scalar, you still get the 0 vector. So this is a subspace. So what are all of the subspaces of R2? If you think about it, there's any line through the origin. There's 0 in all of R2. So the answer is the complete list of subspaces of R2 is just the 0 vector, which is 0-dimensional, any line through the origin, and all of R2. And is that really all the possibilities? So one thing you should think about is, suppose you take a line through the origin and you try and do something different. Maybe add another vector over here. So suppose you took the line through the origin together with this vector. Is that a subspace? Well, I'll let you think about that and see why it's obviously not. And we'll talk about that a little bit in the following section. Okay, let's do a couple of slightly more sophisticated examples. Suppose I was in Rn and I took the following subset. I took the set of vectors a1 through an such that the sum is 0. Is that a subspace? Well, the answer is yes. If you take, what do you have to check? You have to check that if you have a vector where the sum of the coordinates is 0 and another one, and you add them, it still has that property. And that's true. And you also have to check if you have a vector and you multiply it by any scalar, if the sum of the coordinates was 0, then the sum of the coordinates after you multiply by a scalar is still 0. And more generally, what if I took this? Suppose, again, I'm in Rn, and I took a fixed vector v naught to be some vector c1 through cn, and I let w, maybe we'll call it w prime now, to be the set of vectors v in v, such that v dot v0 is equal to 0. The set of vectors which have dot product 0 with this fixed vector v naught. Is this a subspace? Well, let's see. If what I have to check is if v dot v naught is equal to 0, and let's call it v1, and v2 dot v naught was equal to 0, I need to know that that implies v1 plus v2 dot v naught is equal to 0. And I also need to know that if you multiply v1 by r and take the dot product with v naught, it's still equal to 0. Those are the two things you need to check. This tells you that the sum of two vectors in this subspace, or in this subset, are in the subset, and this says that their scalar product is. And both of those are true. So the answer is yes. And the picture is, this is the perpendicular subspace defined by a vector. Maybe I won't try and draw it in R3. Let's just draw it in R2. In R2, you take this v naught to be, say, this vector. Then what are the things that have dot product with v naught? That's this space, which I'm calling w prime, and that is indeed a subspace. So let's look at this example again. The first one I wrote down was W is the set of vectors A1 through AN, such that the sum was equal to 0. Well, what if I took a different equation? What if I tried to set W to be the set of vectors A, such that A1 squared plus 2A2 plus A3 cubed plus dot 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 whatever, AN is equal to 0. Usually such a thing is not a subspace. Not a subspace. Roughly speaking, in general, if W is described by one or more linear equations, then it's a subspace. And Otherwise, it's not usually, except that there's some sort of funny accidents that can happen. Um, if the equations are nonlinear, it's probably not a subspace. So, as an example of the latter, if I took x squared plus y squared equals 1, the set of vectors xy, such that this holds, that's of course the circle, and this is certainly not a subspace. It's not straight, it's not flat. If you multiply any vector by 2, it takes it out of the set, for example. So this is certainly not a subspace. If I took the equation x squared plus y squared is equal to 0, well, even though this is a nonlinear equation, it's kind of a stupid one. The only solution is if you let w be the set of solutions to this, w is just the 0 vector, and that is an example of a subspace. So that's what I mean by some sort of silly accidents can happen, but generally, if you have a nonlinear equation, you expect its solutions not to be a subspace. A particularly important kind of subspace is one described as follows. We've seen some examples of this. Suppose V was the set of all functions on R, real valued functions on R. So this is some big infinite dimensional vector space. And suppose I let W be the set of F such that F double prime plus F is equal to 0. So this is a d f squared dx squared plus f of x is equal to 0. And we did this example. W is the set of A cosine x plus B sine x. And I mentioned that, well, this is a vector space. And I talked about that last time, and now all I'm saying is that this is a subspace of the functions. And that's a common way to construct examples of subspaces, or many subspaces, many spaces arise naturally as subspaces of a space of functions which are given by some kind of equation, differential equation, or other kinds of equations. Now, it's not true, of course, that any typical random equation will give you a subspace of the space of functions. It's only certain kinds of equations. This is an example of one. Okay, well, I've already gone on for a little while, so I'm not going to say too much in this lecture about span. Let me just introduce the concept, and I'll call it a day and come back to that the next time. Suppose you are in R2, and you gave me a single vector v, and said, please find for me a subspace of the vector space containing that vector v. So what I want is W to be a subspace which has v in it, containing well, the obvious one is just the straight line through v. You can take that to be W. So you could take W to be the line through V. But you could also take it to be all of R2. Now, taking it to be all of R2, well, it answers the question. It's certainly true, but it's sort of wasteful. You don't need all of that stuff. And so this W, the line, is the smallest such subspace. And that's the basic idea behind the span. Let's do an example with two vectors. Suppose you're in R2, and I gave you this vector v1 and this other vector v2. Please tell me a subspace of R2 which contains those two vectors. Well, if it's a subspace and it contains v1, then of course it has to contain all multiples of v1, so it has to contain this whole line through v1. And if it contains v2, it also has to contain all multiples of v2. But it also has to contain, for example, v1 plus v2. So it has to contain all multiples of that vector. And it has to contain v1 plus 2v2. And so on. This W, being a subspace, it has to contain, if you take this this v1 and multiply it by a, and then v2 and multiply it by b, it has to contain all of these as a, b run over the real numbers. And you just think about that for 2 seconds. Basically, in this picture, you see that the only way that that can be is if you're getting all of R2. So the general setting is the following definition. Suppose S is a set of vectors. In other words, S is a subset. S is a subset of your vector space V. Then the span of S is by definition the smallest it's the smallest subspace of V containing S. And the prime example, and almost the only one we'll ever talk about really, is where S is a finite set. So S has some finite number of vectors in it, v1 through vm. Then the span of S is what? It's the smallest subspace which contains all of those vectors. Well, it has to contain a v1 if a is any scalar, and it also has to contain, a1 v1. It also has to contain a2 v2 if a2 is any scalar, and it has to contain the sum of these. And so going on like that, it certainly has to contain all of these vectors where a1 through an are real numbers. If the span is by definition a subspace containing these vectors, v1 through vn, so it certainly has to contain the vectors that I've written down here, given by these sums. And that's actually the answer. The span is exactly that collection of vectors that you can obtain this way. So I'll just draw one final small picture over here, and I'll maybe draw it on a new page. Let's do one final example in R3. I'll see if I can do a reasonable, it's not looking good so far, draw a reasonable three-dimensional picture. So here's R3, and suppose I take two vectors, v1 and v2, then the span of them is the plane that they fill out. You take all the sums of vectors, a multiple of v1 times plus a multiple of v2, and that gives you a plane. All right, that's all for now. We'll continue with the notion of span and linear independence next time.